Let's go ahead and start. Recap. So what we started talking about last week was continuous functions. Now intuitively, what's our high level intuition for what a continuous function does? What do we say intuitively that a topology gives us? So you got a set and you give a set a topology. Intuitively, what does a topology give a set?
The minimum amount of structure required to do anything useful.
Not to do anything useful, to do a particularly useful thing,
Okay.
which is capture proximity. A topology is a structure, the minimum structure we need to capture a notion of proximity, of things somehow being close. And so with a topology, we're able to start doing things like calculating limits. We did that a few sections ago. The intuition for the limit of a sequence is what it gets really, really, really close to. We look at the limit of 1 over n, so if we look at the limit as n approaches infinity of sequence 1 over n, so that's 1 over 1, 1 over 2, 1 over 3, 1 over 4, dot, dot, dot. What does that get really, really close to?
0.
0. And so that limit is equal to 0, and that's I think that's one of the ones that we took the time to prove. So a topology is the minimum structure that you need to start talking about things being close to each other. Or it's the structure that gives us proximity. We can start talking about proximity, things being close. The high-level intuition for a continuous function is it preserves proximity. So a continuous function maps from one topological space to another, and it preserves proximity. If 2 points were close in the domain, then those 2 points still better be close in the codomain. So that's what intuitively, from a topological standpoint, that's the intuition for a continuous function. We already talked about the calculus intuition for a continuous function. You can't pick up your pencil when you draw it, right? Our notion is it preserves proximity. Points that were close before the mapping are still close after the mapping. So let's remind ourselves now of this epsilon-delta definition from calculus. The messy one, but the one that comes with the nice picture. So here's a repeat of the exact same definition we talked about last time. The epsilon-delta definition for calculus. What is it? What does it say? It says a function from the real numbers to the real numbers. It's understood in calculus that the real numbers are endowed with the standard topology. So remember, continuity makes 0 sense unless you're mapping from one topological space to another topological space. So f is a function from the real numbers to the real numbers, where both of those have the standard topologies. That function is continuous at some point, x naught, in the domain. If and only if, this is true. If for every epsilon you choose, I can always find some delta such that if x is within delta of x naught, then f of x is within epsilon of f of x naught. And we played this game a few times last time. I would give you an epsilon, your job was to find the delta that satisfied it. If for any epsilon I give you, you could always find a delta that satisfied that implication, then the function was continuous at that point. If I could find a single epsilon, if I could find one value here, such that no matter what delta you chose, you could never satisfy that implication, then the function was not continuous at that point. And so intuitively, here's two pictures looking at this function over here. So here's some function f. Here's some point x naught in the domain. Here's f of x naught. Sorry, chalkboard's kind of dead right there. What this says is no matter how small of an interval, what it says is no matter what interval I place around f of x naught, remember that picking an epsilon was logically equivalent to picking an interval around f of x naught. So no matter what interval I pick around here, you can always find some small enough interval around here such that when you map all these points, trying to do my dotted line here, such that when you run all those points through the function, that was really crooked. Such that when you run that whole interval through the function and look at its output, the output was always inside the initial interval I gave you. So I give you the initial interval. Your job is to come up with an interval around this point such that when you map it through the function, it's inside the interval I gave you. So for this one, it doesn't matter what interval I pick. you can always win this game. So this function is continuous at that point. Now let's go to one where I can win. Notice if I pick some small enough interval, so I pick some small interval now like this. So my interval is right here. Now it's impossible for you to win this game. No matter how teeny tiny of an interval you pick around x0, if we look at how it maps, it's going to map these points okay. So these points right here, those get mapped up, those come in, okay, those points go inside my interval. These ones, they come up, over, okay, yes, they're inside my interval. But your problem's on this side. No matter how teeny tiny you come over here, some of your points are going to map to up here. And they're always going to map outside my interval. And so you're always going to have some points that map outside the interval I gave you, if I pick a small enough interval in this picture. And so you can't win over here. And so the function is not continuous at this point. Notice that this function I drew over here is continuous at this point, it's continuous at this point, it's continuous at this point, it's continuous at this point. There's only one bad point where it's not continuous. So this was talking about a function being continuous at a point. Now we had a definition for what it means for a function to just be continuous. Again, using the calculus notion. A function is continuous if and only if it's continuous at every point in its domain. So we would call this whole function continuous, and we would say that this whole function is not continuous. If there's one point that breaks it, then we say the function is not continuous. So don't get those two things mixed up. There's a difference between being continuous at a point and the whole function being continuous. Two different notions. Okay, so that was a reminder of the calculus way of thinking about it. And then we gave you our topology way of thinking about it. Now, what's the mnemonic sentence we use to remember what continuous means in topology?
The pre-image of open sets are open.
The pre-image of open sets are open. That's what it means to be continuous in topology. Now let's get the definition. Some function from x to y, it's understood that x and y have topological spaces associated with them. Some function from x to y is continuous if, for every open set in y, the pre-image is open in x. If V is in the topology on y, then the pre-image of V is in the topology on x. If V is open in y, then the pre-image of V is open in x. Now it has to be the case for every single open function in y. Run it backwards through the function, then it'll be open in x. Otherwise, we done messed up. Or it's not continuous. Okay, and so we did a bunch of feel-good examples. We did things, we proved like addition is a continuous operation. We proved that multiplication is a continuous operation. We talked about how any polynomial function is a continuous function. So we talked a lot about we did a lot of feel-good examples about functions you're more familiar with, showing that they are in fact continuous. And what we were working up towards is trying to show that the epsilon-delta notion of continuity from calculus, so that's combining this with this. This in calculus is what it means for a function to be continuous. We were trying to show that this is logically equivalent to our topological notion. That's what we were working our way up to. The last thing we ended with last time is we just rewrote the epsilon-delta definition of continuity in topology terms. So this is just rephrasing exactly what this says, but just using more topologically friendly language. And then we're going to prove that this is in fact logically equivalent to this. So let's read through this and see how it's logically equivalent. What does it say? A function f from x to y is continuous if for any x we choose, so this is going to be, notice that the only difference between this definition and this definition is this definition says this has to hold at every x. This says this holds at every x. So we're going to say at every x, if and only if for at every x, this definition holds. That's what we're about to say. So if for at every x, and then the following is going to be what we say up here. And for every open set V, V is going to be an open set in our image. So V is the same thing as picking an epsilon here. For every epsilon, or for every V in Y, for every open set in Y, for every epsilon you pick, where V contains that point, so that was an open interval containing our point f of x naught, there existed some open set in the domain containing x, some neighborhood containing x, or some open interval containing x naught, such that when we map that neighborhood, we're a subset of V. When we map this neighborhood, we're entirely inside this set. So this is pretty much just an interpretation of this. It's not quite a perfect interpretation. We'd have to show that an open set here is logically equivalent to an open ball here. These are obviously basis elements. So there would be a little bit of proving to show that this is exactly logically equivalent to that, but that's a trivial amount of proof. The more interesting thing is what we're going to prove here now. So what we're going to prove now is that f from x to y is continuous if and only if for every little x in x and for every open set in y where that open set contains f of x, there exists some open interval in x such that, some neighborhood of little x in x such that the image of that is a subset of that. So proving exactly what we were just talking about. I'm going to prove that this is logically equivalent to f from x to y being continuous. So f from x to y being continuous is using this definition. Here's exactly what it means to be continuous. And then the rest of this is using this notion of continuity. And we're showing that they're logically equivalent. That's the proof. We understand what we're trying to prove? Okay, so the first direction is going to be real easy. So one, remember, maybe put my arrow here. We're doing an if and only if. I'm showing that if this is the case, then all this is the case, and then if all this is the case, then this is the case. If and only if. So go in the forward direction first. Assume the antecedent, show that implies a conclusion. So I'm going to assume that f from x to y is continuous, and show that implies this thing is true. So what? Let f from x to y be continuous, comma, let little x be any point in big X, and let V be any open set in Y such that f of x is in V. So what am I trying to prove? I'm trying to show that if f is continuous, then for any x and for any open set V where the image of x is in V, then there exists some neighborhood of x such that f of that neighborhood is a subset of V. Okay. 2. Let u sub x equal the preimage of V, and observe little x is in u sub x. So make sure you notice that u sub x is actually a neighborhood of x. So first off, if f is continuous and V is an open set in Y, what do I know about u sub x?
It's an open set in x.
It's an open set in x. So u sub x is an open set in x, and u sub x does in fact contain little x. 3. Then the image of u sub x is equal to, maybe I'll say this, is definitely a subset of itself, but that's equal to V. So I just barely found some set in X, some set in big X, containing little x, such that when you map it, it's a subset of V. In this case, it was the entire preimage of V. So that was easy. I start out with V. Maybe get a rough picture really quick. Here's X, here's Y. I start out with V over here. Here's V. And I know that f of x is in V. Here's X over here. I need to find some open set over here, such that when I map it through, I'm a subset of V. And I just did the whole preimage of V. Because since f is continuous, I was guaranteed the whole preimage was an open set. So that direction was easy. Alright, so now we need to go the other way. Now I need to assume all that stuff. Where's my eraser? Well, maybe draw a picture here on how we're going to do this. So now I need to go the other direction. Now I need to assume that for any little x you choose, and for any open set in Y containing the image of that point, then I can find some open set over here containing a point such that it maps this way. I need to show that if that's the case, then f is in fact a continuous function. So now I'm going to assume these two lines and show that implies f is continuous. So how am I going to do that? I'm going to come over here in Y, and I'm going to pick a random open set. So I'm going to come over here in Y, I'm going to pick some random open set. How in general do we show that a function is continuous?
The preimage of an open set in Y is over X.
Right, I need to pick some random open set and show that its preimage is open. That's how we do it. So I'm going to take W over here, some random open set in Y. And I'm going to pick some random point X over here, some random point little x, such that little x maps into here. So here's f of little x. So I'm going to start out with W, and I'm going to pick some little x such that little x maps to f of x. Well, maybe before I say that, let's say it this way. I'm going to start with W, and I'm going to look at W's preimage over here. So I'm going to have U over here, where U is equal to the preimage of W. So I'm going to have U over here. I'm going to pick some random little x in U, so f of x is going to be over here. My whole job is to show U is open. So I pick W where W is open, and I define U to be W's preimage. I do not know that U is open, because now we don't know that f is continuous. That's what we're trying to prove. So I'm trying to prove U is open. How am I going to prove U is open? I'm going to show that for any point little x you choose in U, I can find some open set containing it, some U sub x containing x, such that U sub x is a subset of U. If I can do that for every little x inside of U, then U will just end up equaling the union of all those U sub x's. For all x in U. If I can show you how for any little x in U we choose, I can find some U sub x containing it, such that U sub x is a subset of U, then the union of all those U sub x's is U. And so U is a union of open sets. And therefore U will be open. So that's big picture how we're going to prove this.
I'm forgetting the name of the theorem that you're using to say that.
It's called the union lemma.
Oh, to say that a union of open sets is open?
Oh, that's by definition of a topology.
The union lemma is the one that you're using to say there's an open set around x within U?
The union lemma says that if I can express U as a union of subsets, if I can express any set A as some union of other sets B sub x for each x in A, and I show that each of those B sub x's is a subset of A, then they give me back A. That's the union lemma. So that's not particular, that's not unique to open sets. That's for sets in general.
Okay, I'm just wondering what theorem you're using to say that there's an open set around x within U in your picture there.
Oh, that's going to be the assumption here. So that's going to be the hard part, is how do I come up with that U sub x? But once we do, then, so yes. I didn't explain very well that that was going to be the hard part. So that's the hard part. Okay, so now we're going this direction. So now, assume for all x in x, and for all v in tau sub y, where f of x is in v, comma, then there exists u sub x in tau sub x, such that x is in u sub x is a subset, x is in u sub x, and f of u sub x is a subset of v. I didn't bother saying x is in u sub x here because that's usually what we mean when we do u sub x. We mean use the neighborhood of the point x. So a little bit more explicit here than what I have written there. So we assume that that's the case. We're trying to show f then is continuous. Okay, 5. Let W be any open set, so let W in tau sub y. So W is any open set in y, comma, let U equal the pre-image of W. So our whole goal is to show that U is open. Maybe we'll separate to the next line, so I should have said and. And let U equal the pre-image of W. So I'm trying to show U is open. So 6. Let little x be any point in U. My job is to find an open set in X containing little x, my job is to find an open set in X containing little x, where that open set is a subset of U. And that union of all those open sets, that gives me U. Since U is a union of open sets, U is open, and so the preimage of W is open. Okay, so let X in U, which gives us that f of X is in, if X is in U, what is f of X in? W. Okay, so now I have an open set containing f of X. By assumption, what does that give me?
There's a neighborhood around X. That's
What we assume is that for any open set in Y containing f of X, there exists some U sub X in our topology on X, such that X is in there, and its image is a subset of V. So that gives me that there exists U sub X in our topology on X now, such that X is in U sub X, and the image of U sub X is a subset of W. Now, if the image of U sub X is a subset of W, then U sub X, what?
is a subset of U.
Is a subset of U. If when I map these points through, if these points in my map are a subset, if these points in Y are a subset of these points in Y, then the preimage of these points is a subset of the preimage of these points. Remember, this is a set in Y, this is a set in Y, this is a set in X, this is a set in X. So if this set in Y is a subset of this set in Y, then this set's preimage has to be a subset of this set's preimage. Okay. Then U equal to the union of all those U sub X's for every little x in U is open in X. 8. Therefore, F is continuous. Right? We just barely showed that the preimage of any open set, namely U, is open, and so that's what it means for F to be continuous. Any questions on that? All right. Ready, set, and move on to the next one. So the next one we're proving, we're going to show that if f is a continuous function, and we have a sequence of points in X that converge to x naught in X, then the image of this sequence converges to the image of this point. So let's get a picture of that really quick, what we're trying to show. Here over here is X. Here over here is Y. We've got some sequence of points over here. And they converge to get closer and closer to this point x naught. So this sequence right here is what we mean by xn. Some sequence of points, Here's x sub 1, here's x sub 2, here's x sub 3, here's x sub 4, There's infinitely many of them. And they converge to x naught. then when I look at the, and we have f maps like this, and f is continuous. When we look at the image of all those points over here, so maybe the image of the points over here looks something like this. And then narrowing in on that point, here's f sub x naught. And this sequence right here is f of, the sequence right here is the sequence f of x sub n. So we take this point, run it through our function, it spits out right here. We take this point, we run it through our function, it spits out right here. Dot, 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 all these points spit out, spit out, spit out. If these points are getting closer and closer to here, then these points better be getting closer and closer to here. Because continuous functions intuitively preserve proximity. Let's just think about that for a sec, coming back to this picture. Coming back to this picture, this one that's a broken picture that doesn't work. Topologically speaking, how do we instantly know that this function is not continuous? Because in our domain, with the standard topology, remember, here we have R with the standard topology, and here we have R with the standard topology. And we're taking a point here, and we're mapping it up through and sticking it here. We're taking this point here, we're mapping it up through and sticking it here. So we're taking all these points, and we're sticking them somewhere in here. Notice that this point, x naught, and the point just to the right of it, right there, are next to each other in this topology.
Yeah.
When I map them through my function, this one got put here, but this one got stuck clear up here. They are no longer next to each other in this topology on Y. They were next to each other here. They're no longer next to each other here. This function did not preserve proximity. Points that were close here were no longer close here.
How do you define that something is next to another one?
That's why I did this.
I'm assuming when you say next to, you mean like there's nothing in between. Well,
No.
So, okay, sorry, it's intuitive.
Arbitrarily close to. That's a better way to say it. For any positive distance you pick, it was within that positive distance of x naught.
I mean, I get the intuition, but I don't know if I actually.
There's not a good way to say it. The best way to talk about proximity is with limits.
I just don't know how I could logically say they're not next to each other.
Logically, there's no point next to another point.
Exactly, so it's like, I don't know.
That's why we do next to.
Okay.
When
if I
we
do
say that, we
remember,
just mean arbitrarily close to. You pick any small number you want. I can always find a point within that small distance.
they're outside of the window of the y, and that's the only thing. The function x, whatever, is outside that window. It's the only way I can argue that it's not next to, essentially, right?
If I took a sequence of points coming this way that got arbitrarily close to x naught here, when I map it through and I take that same sequence of points, they're no longer going to get arbitrarily close to f of x naught. They're going to get arbitrarily close to this circle point up here.
Yeah.
So a sequence of points that was getting arbitrarily close to x naught here are no longer necessarily getting arbitrarily close to f of x naught here when I map them through. So thinking about proximity, the proper way to do it is think about it in terms of limits. It's just not a very intuitive way to do it. So I got to choose precision or intuition. And I try to remember to do that when I technically lying to you. Okay. But here we go. So proving this one. You have big picture what it is we're trying to prove. Now maybe let's remind ourselves of what it means for a function to converge to a point. What did it mean when I said that the limit the limit as n approaches infinity of some sequence x of n, what does it mean when I say that's equal to x naught?
It means you can find a big N such that every point in the sequence is, well,
You remember it's spreading them out. Okay. It says that for any u sub x naught we choose, for any open set containing x naught, there exists some big N in the naturals such that x sub n is in that neighborhood, u sub x naught, for all little n greater than or equal to big N. So what it means is pick any open set containing x naught that you want. Make it as small as you want. Obviously, I can't draw it too small, otherwise I won't be able to see it. We'll draw u sub x naught up here in brown. So here's our u sub x naught. There it is. For any u sub x naught you choose, there must exist some point in the sequence such that from that point onwards, it's always inside u sub x. So in this case, it was what? 1, 2, 3, 4, 5, 6, 7, 8, 9, maybe 10. From index 10 onwards, we were always inside there. Now I didn't have to find the first one. If it's in there from 10 onwards, it's also in there from 20 onwards. It's also in there from 2000 onwards. It's also in there from 200 trillion onwards. We don't need to be tricky and get all the first point that's always inside there. We just gotta find one. Because a sequence is infinite. Intuitively, what I'm saying is, eventually, infinitely many terms of the sequence are all going to be inside of there. There's going to be a finite number outside, all the infinite rest are all going to be inside. Okay, so that is what it means for a function to converge to a point. Or sorry, sequence. Don't let me accidentally lie to you. That's what it means for a sequence to converge to a point. That's what it means for the limit of a sequence to approach a point, or for a sequence to converge to a point, same thing. So here's what we know. Is this an if and only if?
No.
Probably because one way is hard. I think this should be if and only if. But maybe the author wrote it this way because one of the ways are hard. And it's not the focus of this class. This would be the focus of an analysis course. But, so which way are we trying to show? We're trying to show that if this converges, then this sequence also, over here also converges. So we know that, so we're given a sequence x of n that converges to x naught. I'm given that f is continuous. My job is to show that this sequence over here converges to f of x naught, right? That's what we're trying to show. So how am I going to show that this sequence over here converges to f of x naught?
You'll find some neighborhood of x naught.
Right, so I'm going to pick some random neighborhood of f of x naught over here. Call it v of f of x naught, or maybe v of y naught. Maybe we'll use v sub y naught, where y naught is equal to f of x naught. So we'll just name that point. So v sub y naught is going to be some neighborhood, some open set containing f of x naught, right? What do I know about the preimage of v of y naught?
It's an open set in x.
It's an open set over here. So then I know if I look at the preimage of v of y naught, we'll call that u sub x naught. That's going to be an open set over here. Since y naught is in v, x naught has to be in this u. So this is an open set containing x naught. But I know that the sequence xn converges to x naught. So then I know that there is some index such that from that point onwards, this whole sequence is inside here. But if from some point onwards, this whole sequence is inside of here, then the image of this sequence has to be inside of here. Right? And then so, it's going to converge. So that's going to be the logic. There's a picture. Let's actually write it out now. All right. So 1, let f from x to y be continuous. Remember, if we say it's continuous, it's instantly understood that there's a topology on x and y. Comma. And let xn be a sequence in x such that the limit as n approaches infinity of x of n is equal to x naught, comma, and finally, and let y naught equal f of x naught. Right down here. And let y naught equal f of x naught, since we're going to need to reference that point a lot. And I guess we could also say this, comma, and let the sequence y sub n equal the sequence f of x of n. So we'll just call the image of everything all our x's over and y's y's. And then that'll probably help keep things a little bit more clear. Okay. So what is our job? Our job is to show that the limit as n approaches infinity of y sub n is equal to y naught. I know x sub n converges to x naught. I'm trying to prove y sub n converges to y naught. That's what we're trying to prove. Okay, 2. How do I show that y sub n converges to y naught? I need to show that for any neighborhood of y naught you choose, I can always find some index such that from that index onwards, our whole sequence is inside that neighborhood. So let v, we use these when we're talking about open sets in y, let v sub y naught in tau sub y such that y naught is in v sub y naught. So let v be any open set in y containing y naught. And let u sub x naught equal its preimage of v sub y naught. Sorry. So u sub x naught is a preimage of that. Then u sub x naught is an open. How do I know that u sub x naught is open?
Because it's continuous.
Because f is continuous. So the preimage of open sets have to be open sets. So I know u sub x naught is open, and x naught is in u sub x naught. Obviously, because y naught was in v sub y naught. Okay. So I know that u sub x naught is an open set containing x naught. And I know that xn converges to x naught. So that, what does that give me?
U big N.
Yeah, so then there must exist some big N, some index, big N, in the naturals, such that x sub n is in u sub x naught for all little n greater than or equal to big N. Since xn gets arbitrarily close to x naught, then starting at some index, all our terms have to be within that open set containing x naught, that neighborhood of x naught. 5. Then y sub n is in v sub y naught for all n greater than or equal to n. If all our x sub n's were in the preimage, then all of the image of all those points has to be in the image. And that's exactly the definition of the limit. 6. Then the limit as n approaches infinity of y sub n is equal to y naught. And we're done. So if a sequence converges in the domain, that same sequence converges in the codomain, as long as the function is continuous. Which intuitively makes sense because we know continuity means proximity is preserved. And that's what limits are all about capturing, proximity. Okay, next one. Bit easier one that doesn't require as much thinking. So we know that a function is continuous if and only if the preimage of open sets are open. What if the preimage of closed sets are closed? Then do we know a function is continuous? So the next theorem we're going to prove is that a function is continuous if and only if the preimage of closed sets are closed. So f from x to y is continuous if and only if for all c that are closed in y, its preimage is closed in x. Probably should use D. We've been using D's for closed sets in y and C's for closed sets in x. So let me switch those to D's. Okay, and we got to prove this both ways. So I got to show if f is continuous, then this is the case, and then I need to show that if this is the case, then f is continuous. So first, we got to go this way. So 1, that's assuming f is continuous, right? Wrong one. Let f from x to y be continuous, comma, and let d closed in y. So I know f is continuous, and I grab some set d that's closed in y. I'm trying to show that its preimage is closed in x. Okay. 2. Then, what's the best way to say this? Then the preimage I'm not sure if I want to introduce a v into this or not, or just use d complement. How best to say this? Okay, I'm spending too long thinking about converting it 100 times by now. So let v equal d's complement. So v is the complement of d. And what do we know about v?
It's open.
It's open. By definition, what does it mean for a set to be closed? Its complement is open. Okay, 3. Then the preimage of d, well, that's the same thing as the preimage of y minus v.
Yeah.
That's everything in y that's not v is the same thing as d. D is v's complement. D is everything in y that's not v. V is everything in y that's not d.
Using the C, is that the same as just?
Oh, did we use that not before?
I don't recall.
What did we use for?
Didn't we do the line
We'll
on
just
top?
flat out say it this way. V is equal to y minus d. It's just d's complement. Everything in y that's not d.
Okay,
I think we did the upper C for complement. Because we couldn't use the line because we use the line for closure. Right? When I do A like that, that's A closure, not A complement. So I think we were using little c's for complement, but we'll just write it that way.
if you did, I must have read.
Clears up everything. Okay, now we're going to use a theorem all the way back from the preliminary stuff, which is that the preimage of a difference of sets is the same thing as the difference of the preimages. The preimage of a difference is the same thing as the difference of the preimages. It's going all the way back to chapter 0, preliminary stuff. So then that is equal to, what's the preimage of y?
X.
All of x. What's the preimage of f? Well, we'll just call it u, where u is open in x. Right?
Yep.
4. Then C equal to x minus u, which is equal to the preimage of d, is closed. So I know the preimage of d is equal to x minus u. But u is open. And so the complement of an open set is a closed set. So let C be the complement of u, which is the preimage of d, is closed, because it's complement of an open set. Okay, so now let's go the other way. 5. Assume that for every closed set D in Y, comma, F inverse of D equal to C, well, we don't need to name it. The preimage of D is closed in X. So now we're going to assume that the preimage of closed sets are closed. And we're going to see if that forces F to be a continuous function. Okay. How do we show that function is continuous?
The preimage of open sets are open.
The preimage of open sets are open. So let V be open in Y. Now we're almost going to go through the exact same logic here. 7. Then the preimage of V is equal to the preimage, let V be open in Y, comma, and let D equal its complement, Y minus V. So D is its complement. So then the preimage of V is the same thing as a preimage of Y minus D. V is the complement of D. D is the complement of V, V is the complement of D. Did I write this backwards? Let D equal Y minus V, that's the same thing as V equals Y minus D. They're just complements of each other. Okay, so then, once again, oh sorry, that's a minus 1. The preimage of a difference is the difference of the preimage. So this is equal to the preimage of Y minus the preimage of D. What's the preimage of Y? X. What's the preimage of D? We'll call it C, but what do we know about C?
It's closed.
It's closed. How do you know that?
We assumed it in line.
By assumption. We said assume that anytime D is closed in Y, its preimage is closed in X. So since D was closed in Y, its preimage C is closed in X. So then this is equal to X minus C, where C is closed in X. In case you lost track of where we are. 8. Then the preimage, well then we'll just say this. Then U equal to X minus C, which is equal to the preimage of V, is open. Because it's the complement of a closed set. Since C is closed, X minus C is open. So U is the preimage of V, and U is open. So we should show that the preimage of any open set is open. So 9, therefore F is continuous. And we're done. Any questions on that one?
I kind of have a question on about the proof.
Okay.
Sets can be both open and closed. I feel like I've asked you this before, but that's true, right?
Uh-huh. 2 trivial examples are if I know that X tau is a topological space, so nothing to do with this proof up here. 2 sets I instantly know are both open and closed are the empty set and the entire set X,
Right.
because they're both open.
Yeah.
Anything else before I erase it? Okay. So now our next one is proving that function composition, that the composition of 2 continuous functions is a continuous function. Do you remember what what function composition is? What it means to compose 2 functions together?
Roughly.
Huh?
Roughly, yeah.
It's just you do one function after the other,
Oh, yeah.
right? So F might map from A to B, and G might map from B to C. Then G after F, G composed F, maps from A to C. So it's just combining 2 functions and doing it all in one go.
Gotcha.
Roughly the picture we have for it is so we're going to have X here, we're going to have Y as some set here, we're going to have Z as some set here, we're going to have F maps from X to Y, and then have G maps from Y to Z, and then our function, G after F, or G composed F, is going to map from X to Z. I'm going to show that if this is continuous and this is continuous, then this whole thing is continuous. That's how we're showing. Okay. This one. So 1. let f from x to y and g from y to z be continuous. And I'm trying to show that g composed with f, this whole function here, is continuous. How do I show that this whole function is continuous?
For image of set and 0 in X.
I need to pick some random open set here.
Open set, sorry.
Yeah, so pick some, we can use closure if we want now, I guess, but pick some open set here. Look at its pre-image here.
Wouldn't you have that as like a negative 2 or something? Say pre-image.
Well, this is just one function.
Oh, okay.
So it's just a pre-image of one function, or of one set under a function. It's the same way that 2 plus 6 is one number. I just broke it up and happened to write it as a sum of two numbers. I could take a function, I can represent it as a composition of two different functions if I want.
That's a great way to do it.
Yeah, it's just an operation on two functions that spits out one function. An operator on two numbers that spits out one number. Okay, we'll kind of keep that there as long as until we need the space, just to help us think. Okay, so let that, let W be open in Z, comma, and should I name this thing? Just and let W be open in Z. And we'll just look at its pre-image. 2. So then we are looking at the pre-image. So G composed with F, we're looking at the pre-image of this function when we run W through it. Now, when you're undoing the function, you undo the G, then you undo the F in composition. So I'm not going to prove that this is the case, but this is the same thing as F inverse of G inverse of W. Okay, so then this is going to be equal to F inverse of V, where V is equal to G inverse of W. And now what do I know about V?
Open.
Yeah, V is open in Y. Because G is continuous. So I look at the pre-image here, that gives me V here. And since G is continuous and the pre-image of W, which we're calling V, is continuous. Or is open, sorry. Then F inverse of V equal to U is open in X. Oh, I never said that V is continuous. Then that is equal to that, where V is a pre-image of G, comma, and V is open in Y. Okay. Then when we run V backwards through F, call it U, that is guaranteed to be open in X, because F is continuous. So for then U equal to G composed with F inverse of W is open in X, which gives me that G composed with F is continuous. Okay, so we proved that function composition is in fact continuous. All right.
Well, just out of curiosity, what would be an example of a non-continuous function on that two-dimensional plane?
A non-continuous function on the two-dimensional plane.
The planes you're giving us.
Sets.
Yeah, the sets. If you give it the visual representation, just out of curiosity, what would it look like to not?
I'm not visually representing the functions here. I'm just telling you the function maps these points to those points. Whether the function is continuous depends on the definition of the function. Like, I'm not showing you the details of this function. So I'm not pictorially representing the function. So there's no pictorial way to see, oh, that function's not continuous. Over here, there's a pictorial way to see it.
Yeah.
But I'm explicitly writing out exactly how the function maps. I'm saying it takes this point and it maps exactly to this point. Over here, I'm not telling you any way about how f maps. So there's no way for me to pictorially capture, oh, f is continuous, g not so much. Because you have no details on those functions. Because I'm also not giving you any details on the topologies on these things.
Yeah, yeah.
So just a picture to help us understand the logic we're using here. Any other questions? Okay, so notice what we've shown is continuous so far. So we've shown that any polynomials are continuous.
We didn't prove that.
We didn't prove that, but I gave you, we worked up everything you needed to prove it. We showed addition was, and we showed multiplication was. It would have just been a quick inductive proof. Just didn't want to do the proof by induction. So we know that polynomials are continuous. Now we just barely showed that function composition is continuous. So I can take functions inside of functions, and as long as I know that the first function was continuous, and plug it inside of another function that I know is continuous, composing them together gives me a lot of things. There's a lot of functions that you can represent as a composition of two types of functions. So, for example, I know that the function 3x squared plus 2x is continuous. And I know that the function, I may know that the function 1 over x, I might pictorially see this is continuous everywhere except 0.
Yeah.
So now, if I compose these two together and we look at the function 1 over 3 over x squared plus 2x, I also know that that's going to be continuous everywhere except 0. Where this is 0.
Oh, yep.
And so function composition already starts giving us a lot of what we can, a lot of functions we can start talking about, is that continuous or not?
Okay.
And so there's a lot of functions that you can already start looking at yourself and start saying yes, no. Well, at least yes. Maybe you don't know how to rule some out, but there's a bunch that you should instantly be able to start identifying that you'd see in like a regular algebra course or whatever. So that's why showing function composition is so powerful. Take two simple functions that you already know are continuous, put them together, you're guaranteed the result is continuous. Okay, next we have the pasting lemma. How does the pasting lemma work? Kind of an interesting one. So I'm going to start out with x here. Here's x, and I'm going to take a closed set this time in x, call it A. So here's A. So we'll do A there. I'll do B in brown. I'm going to take another closed set, or I'll do B in blue. Here's another closed set, B. And I'm going to pick A and B so that their union gives me all of x. And then I'm going to have two functions over here, mapping over to some set over here, y doesn't matter. So y is somewhere over here. I'm going to have one function, f, that is going to map A into y. And I'm going to have another function, g, that maps B into y. And if f is continuous and g is continuous, and they both map these overlapping points the same way, I can't have f maps this point here up here while g maps it down here. If I pick some point that is in both A and B, then both f and g have to map it to the exact same point. So if we have two functions set up this way, then we have a way of gluing the functions together into one continuous function. Is pretty much what we're saying. So they operate on two different domains, but where their domains are the same, their domains can overlap, and if their domains overlap, they map it the same way. Then there's a way to glue these functions together, paste them together.
We're saying if they map.
If they do. So let's read it exactly. So let X have some topology, and let A and B be close sets in X such that A union B gives you back all of X. If F maps from A to Y, and G maps from B to Y, and they're continuous, and if F of X is equal to G of X for every X in their intersection, so if X here, if X is a point in their intersection, then over here, this is both F of X and it's G of X. They map it the exact same way. So F of X is equal to G of X, they map the same way for all little x in the intersection. Then we can create this new function, h of x, which just maps using f of x if our point came from A and uses g of x if our point came from B. And our resulting function, pasting these two things together, is also going to be a continuous function. And then once we do that, we'll see a quick example of why this is so useful. So maybe try and keep that picture up as long as we can and start proving this. Any questions on what we're proving before we jump in? Okay, so 1, let A, B be close sets in X such that A union B equals X, comma. Let F from A to Y and G from B to Y be continuous, comma, and assume that for all little x in the intersection, A intersect B, comma, f of x is equal to g of x. Okay, there's a mouthful. And define h of x. 2, let h of x equal what we have written down here. Don't want to rewrite that. Okay. 3, I'm trying to show that h of x is continuous. How do I do that? Always and forever, how do we show a function is continuous?
Preimage of open sets are open.
Preimage of open sets are open. So, pick some open set over here. Let V be any open set in the topology on Y. Comma. Then the preimage of V is going to be, oops, we're using H. So then the preimage of V using H is going to be the preimage of V using F union together with the preimage of V using G. Because H just maps however F and G do.
Yes.
So the preimage of all those points under H is the same thing as the preimage of all those points that F gives you and the preimage of all the points that G gives you. Ooh. Did I want V to be closed? I think I want V to be closed. Sorry. Hopefully I want it to be closed. 3. Let D be closed in Y, comma, and observe that the preimage of D is equal to the preimage of D under F union together with the preimage of D under G. And if we can show the preimage of D is closed, same thing as showing F is continuous. So we can use open or closed sets here as we want. I just want to be intersecting this with A's and B's, and I know A's and B's are closed. So I want to intersect closed sets with closed sets rather than intersect open sets with closed sets. Because I know the intersection of two closed sets is closed.
Wow.
Right? Okay. 4. Then oh, maybe I lied. Because I still need it. No, I can still say that. The preimage of a closed set. Okay. Going back to an older theorem that we did. Notice that F, the here's how I'm trying to say this. Then F inverse of D is going to equal, I'll call it C1 intersect A, where C1 closed in X. So here's how we're making this argument. We're looking at the preimage of a closed set from A. I know that the preimage of a closed set is closed, since F is continuous. And so it's going to be a closed set in our domain. So it's going to be a closed set in the subspace topology on A. What is a closed set in A? It's a closed set in X intersected with A. Okay, so the preimage of D is going to be some closed set in X intersected with A. And similarly, the preimage of G is going to be some other closed set in X intersected with B. Oh yeah, we did that. Same logic, same reasoning. Okay. So finally, then H inverse. So I think, yeah, I didn't want to go too close. So 5. Then H inverse of D is going to equal this union this. It's equal to C1 intersect A union C2 intersect B, which is closed in X. The intersection of two closed sets, closed. The intersection of two closed sets, closed. The union of two closed sets, closed. So we got a closed set. So we showed that the preimage of closed sets are closed, therefore H is continuous. Okay, that's the pacing one. Now let's really quick see one. There's lots of useful things that we get it, but here's one obviously useful thing. Notice the absolute value function can be defined as just x if x is greater than or equal to 0. And we can say negative x if x is less than or equal to 0. In the standard topology on R, x by itself, that's just a polynomial. So we know that's continuous. Just a straight line.
Yeah.
Right? So that is continuous. And it's definitely continuous on the closed interval 0 to infinity. Negative x, that's just a polynomial, so it's continuous. And it's continuous on the closed interval negative infinity to 0.
Now would that be a closed interval? What would the complement of that be?
Well, so if all the points less than or equal to 0, its complement is all the numbers greater than 0 to infinity, not including 0.
Well, I guess you can't put it in there.
Maybe to make it really explicit here, let me write it a more topologically friendly way. Where x is in 0 to infinity, and this is where x is in negative infinity to 0.
You just double.
We have an overlap on what to do with 0. But our function said, as long as our two functions do the same thing when you plug in 0, you're good.
Right.
So notice, is this continuous on this interval? Yes. Is this continuous on this interval? Yes. Last thing we need to check. In their overlap, do the functions give us the same thing? The only place that they overlap is at 0. This one spits out 0, this one spits out negative 0. Negative 0 is 0. And so yes, it works. And so now we know absolute value of x is a continuous function. Using that with our previous theorem, I now know something like this. The absolute value of 3x cubed minus 27x plus 15x squared. That whole thing is a continuous function. This is taking a polynomial and composing it with the absolute value, and then we plug that in for another polynomial. Or, well, we add on another polynomial. We know that's continuous. We know addition preserves continuity. And we're good. Okay. So, whole host of things that we can now show are continuous. All right. Glad we didn't try to squeeze that in at the end of last lecture. That took more time than I thought. So that ends continuity. And now we move on to the next section. The next section is on homeomorphisms.
Donnie, I'm gonna have to leave early.
Okay. Haven't moved the camera. Okay. So remember intuitively what continuity gives us. It means if points were close before we mapped, if points were close before we map, then they're close after the mapping. It preserves continuity going from here to here. Let me give you one just really quick. Let's imagine that we're mapping I really quick to the circle. So I is the closed interval, right? Pictorially, we think about it like that. Going back to when we did quotient maps, and we map this to the circle. And the quotient map was to identify these 2 points as the same point. So going from here to here, if f does this, f is going to be a continuous function. Notice that pick any 2 points over here that are close. That point and that point are close. In the mapping, they came out right here and right here. Pick any 2 points that are close over here. When we map them through this function, they're still close. Right?
Does that change if we stretch the line?
Yeah, we didn't give the same sort of size. If you stretch it out, points that are close are still close. Yep. Think about it like a rubber band. And think about close as the atoms actually touching each other. As long as you don't break the rubber band and you stretch it out, the atoms that are connected are still connected.
Yeah.
Oversimplified, but gives you an idea, gives you intuition. Okay. So stretching doesn't change anything. Okay. But anyways, so going from here to here is continuous. The other way, going from here to here, is not continuous. Because these 2 points, right here and right here, were these 2 points.
Yeah, that's right.
And so they were close here, but now they're not close. So going from here to here is not continuous. Going from here to here, there was a way to do that continuously. There's no way to go from here to here in a continuous manner. You got to cut somewhere. So almost all the points are still going to be right next to each other. But suddenly there's going to be 2 points that aren't anymore. That's intuitively how to think about it. So continuity preserves proximity one direction. A homeomorphism preserves continuity, or preserves proximity both directions. It's the first thing that we're going to come across that somehow says two topologies are somehow the same. And so it turns out this is not going to be homeomorphic to this. They're going to somehow be different. However, this is going to be homeomorphic to something that looks like this. Because there is some mapping I can do from here to here, such that proximity is preserved both ways. Okay, so that's the intuition. Let me move the camera. Glad I thought of that. And then we'll move on to the next section. Good enough. Okay. So, moving on to homeomorphisms. Let's jump into the definition and then see what we need to fill. Alright, so let x and y be topological spaces, and let f be a function from let f as a function from x to y be a bijection. Remember what a bijection is?
It's a function that's 1 to 1 and onto.
It's 1 to 1 and onto. It maps every point to one and only one point, and it doesn't leave any points out. It maps everything in X to everything in Y, and there's no double pairings. Every X gets mapped to one and only one thing in Y.
Yep.
That's a bijection. So a bijection is a homeomorphism provided that both F and F inverse are continuous.
Yep.
So it maps in a continuous way, and if you look at it backwards, it's still continuous. Both the function and its inverse are continuous.
Right.
That's what it means to be a homeomorphism. Or, one of the high-level ways that we think about it is it maps each point in the first set to one and only one point in the second set, and it maps each open set in the first over here to one and only one open set over here. So it does this pairing off both of points and of open sets.
Okay.
So that's a high-level way that we think about a homeomorphism. So I'm often just going to write HOM for homeomorphism or homeomorphic because it's an absurdly massive word. So F is homeomorphic if and only if it's a bijection on points and open sets. That's just intuition. It's not a definition. Here's the exact definition. So read it one more time and then think we'll be good. So let X, Y be topological space and let F from X to Y be a bijection. Then F is a homeomorphism provided that F and F inverse are continuous. If there exists a homeomorphism between X and Y, then we say X and Y are homeomorphic, or X is homeomorphic to Y. And we write it this way. X is homeomorphic to Y. They're in some sense the same. This does not say every function from X to Y is a homeomorphism, if these two are homeomorphic. It says there exists a function from X to Y. That's a homeomorphism.
Gotcha.
That's what it means for X to be homeomorphic to Y. There is some function you can come up with that's a bijection, that's continuous, and its inverse is continuous. That's what it means for them to be homeomorphic. Okay, so that's a lot to swallow. Let's get down to a very nitty-gritty, concrete example, see everything in action, and come up with our homeomorphism. So here's X, A, B, C. Here's its topological structure. Here's Y, 1, 2, 3. Here's its topological structure.
Okay.
Notice that X and Y have pretty much identical topological structures.
Yes.
So it turns out that they are going to be homeomorphic.
Okay.
Which means that I should be able to come up with some function, f, from X to Y, that's a bijection, that's continuous, and its inverse is continuous.
Uh-huh.
So I better be able to do that if this X is in fact homeomorphic to Y.
Uh-huh.
So let's come up with it. What is a mapping I should use? What should I map A to? What should I map B to? What should I map C to? Such that F is a homeomorphism. Well, let's try something dumb first. Let's map A to 1, B to 1, C to 1. Okay, is F a homeomorphism between this set and this set?
No.
No, it's not even 1 to 1. It's not 1 to 1, it's not on 2, so it's not a bijection.
Okay.
Forget continuity, throw continuity out the window. This isn't even a bijection. We have A mapped to 1 and B mapped to 1. You can't have that if you're going to have a 1-to-1 function. Okay, so maybe this time we try 2, 3, 1. Okay, let's try that. First off, is F 1 to 1?
Yes.
Yes, only one thing mapped to 2, only one thing mapped to 3, only one thing mapped to 1. Cool, it's 1 to 1. Is it on 2?
Yes.
Yes, we used up all of Y. We mapped something to 1, we mapped something to 2, we mapped something to 3.
But 2 is not, 2 by itself is not an open set. Why is it?
So now, we need to pick open set here, and look at its pre-image, and see if it's open here. Let's see if F is continuous.
So were we just looking at points before?
Well, just taking it one step at a time. Is F continuous? So let's check. So, let's look at the pre-image of the set containing 1.
A, which is open.
The pre-image of 1 is C,
Oh, yes, sorry.
which is open.
Yes.
Okay, that worked. What about the pre-image of 2? Oh, 2 isn't an open set here, so don't check its pre-image. 3 by itself is an open set here, so let's check its pre-image. What's pre-image of 3? Just B. Is B open?
No.
No. So F is not a continuous function.
Okay.
What?
So you couldn't have any continuous function by this. You couldn't have any continuous function with that topology.
So the pre-image of just, which one were we doing? 3? The pre-image of 3 using this mapping.
Yes.
The pre-image of 3 is just going to be the set containing B.
Yes.
You with me? The set containing just B is not an open set over here. This pictorial representation is saying all my open sets are the set containing A, the set containing C, the set containing AC, and the set containing ABC. So the set just containing B is not open over here.
Right.
So the set containing just 3 is open over here, but its pre-image is not open over here. So F is not continuous.
Can it be continuous? Any arrangement that we give it?
No, you got to find special functions. That's what I'm saying. In general, if I just have x and y, even if it's obvious to us, okay, these are homeomorphic, that's the same topology, you can't just pick some random function between them and expect it to work. You have to find the function. Maybe there's a couple of them. There could be more than one function. But you can't just go around aimlessly filling out numbers and expect it to work.
Okay.
So now, here's one that happens to work. 1, 2, 3. A behaves the exact same as 1 over here. B behaves the exact same as 2 over here. C behaves the exact same as 3 over here, topologically speaking. And so this is in fact going to work.
Okay. Yeah.
And so would 3, 2, 1 as well, right?
And so would 3, 2, 1. So we could have also used 3, 2, 1. That would also work. Because topologically speaking, there's no difference between A and C.
Right.
So I could have even made this a function from x to x. We can talk about x being homeomorphic with itself. And I could have mapped A goes to, relabel this ABC. And I could have done A goes to C, B goes to B, and C goes to A.
Yeah, that would work.
So that's one way to show that x is homeomorphic to itself. Now I could have also just mapped A to A, B to B, C to C. It's always going to be the case that a topological space is homeomorphic to itself.
Right.
Because you map every point to itself. And that's the point that behaves the same as itself.
Yeah.
So that's trivial, but you were noticing that A and C are somehow topologically equivalent over here. And so yeah, that's how we catch that. Okay, so that is a very concrete example of showing that two topological spaces are homeomorphic. The same. So that's what means for them to be the same. Now notice that, how do we show that two topologies are homeomorphic? We have to find a homeomorphism between them. That's the only way. We've got to find the function. We've got to be able to find the function that does the mapping in this way. It's 1 to 1, it's on 2, it's continuous, and its inverse is continuous. So that's how you prove two topologies are homeomorphic. How do you prove two topologies are not homeomorphic to each other? That's much harder. You have to show that there is no function you can find that does this.
Yes, right.
So it's much easier to show that they are homeomorphic to each other than that they're not homeomorphic to each other, as a general rule.
Gotcha.
Because you could run for infinity. Well, I guess
Right, a very dumb way would be to iterate all over all infinitely many functions.
Right.
Maybe there's a finite number. In this case, there's a finite number. So if you're lucky and there's a finite number of functions, yes, you can iterate over all of them and check each one.
Well, that's not gonna work.
And then say there was no possible function. Yes, that's one way to do it. Okay. So from here on out, that's going to be the feel with some of the graphs that we're drawing. It's going to be, we got to come up with that function. And from here on out, most of this chapter right today, I think we have one proof at the end if we even get to it. We're getting back to a feel-good chapter. Intuition type chapter. I guess I'll prove each of these, but they're small proofs. So this is another intuition feel-good chapter. Lots of pictures, lots of concrete examples.
Okay.
Not so heavy in theory. Okay. So let's look at another function. More concrete one. Again, I'll look over here at the function from R to R, where R has a standard topology,
Okay.
by f of x is equal to 3x plus 1.
Gotcha.
So notice what this function does. So we're talking about 3x plus 1, so it has a slope of 3 and it goes through the y-intercept at 1. Right? So it's going to look something like this. Now notice what it does to any interval that we run through this function. If I take any interval from a to b here, any open interval, and I run it through this function, then this maps up to right there, but this maps up to right there, right? Let's pretend that I'm running the numbers 1 to 2 through this thing. So this is a function f of x is equal to 3x plus 1. So when I run 1 through it, what's f of 1?
It's 4.
It's 4. Maybe let's run 0 through 1. I think it'll make it most clear. So forget my picture. Let's just run 0 through 1 through this thing. So I'm running 0 through 1 through this function. When I plug 0 into the function, what do we get? 1. When I plug 1 into the function, what do we get? 4. So if we ran the interval 0, 1 into the function, when we plug that into the function, so f of that whole interval, 0 to 1, spat out the interval 1 to 4, right? So it takes this interval, and what did it do? It shifted it 1 unit to the right and then stretched it to make it 3 times bigger. That's a topological way of thinking about this. As, you know, shifting and stretching things, topologically speaking, doesn't change anything. So that's the intuition for what we just did. We grabbed that little interval right there, we shifted it over 1, and we stretched it out by a magnitude of 3. It doesn't change anything. Now we can check that this is, in fact, this function is a bijection. That's a trivial thing to do. Notice, first of all, that, we can check that this is a homeomorphism. So this function right here is a homeomorphism. Let's check. First off, is it 1-to-1?
Yes.
Yes. If you tell me the output, I can tell you the associated input.
Yes.
Every output comes from one and only one input. That's what it means to be 1-to-1. So if I were to tell you, I'm not going to tell you why I plugged into the function, but 4 came out. What did I have to plug into the function if 4 came out? 1. 1 must have been the number I plugged in if 4 came out. So that's what it means to be 1-to-1. Every output comes from one and only one input. I don't have 2 inputs giving me the same output. So this function is 1-to-1. Or in other words, just look at its inverse. Is its inverse a function?
Yeah.
Yeah. So if its inverse is a function, then the function is 1-to-1.
Wait. Really?
Yes.
Yeah, of course. That makes more sense.
Right. And you know how to find the inverse of the function?
You just undo the function.
Yeah. So erase the picture now for a second. So I'm trying to find the inverse of this function. The inverse of the function, let's do it in a concrete example. In a concrete example, I asked you, okay, let's say I want to know what output spits out, pick a number here.
2.
2. I want to know what x spits out 2. So I want to know what x is equal to 2. What do? You basically solve for x. I take the 2, I subtract 1, and I divide by 3.
Yeah. Yep.
So in general, to undo it, I took my number, subtracted 1, and divided by 3. So in general, if we want to figure out the x to get a particular y, what do?
X minus 1.
I subtract 1 and I divide by 3.
Yeah.
So that's all I'm doing here. That's the preimage. Let me write it, not preimage, that's the inverse function.
Inverse.
So the inverse of this thing, f inverse of x, is just equal to x minus 1 divided by 3,
Yeah.
which is the same thing as 1/3 x minus 1/3. Same thing, right?
Yeah.
So looking at f for a second, I know that f is 1-to-1. I know that's on 2.
And
How do we know it's on 2? I can get any number you want. So we will map every real number to every real number. No real numbers are left out.
right.
We can eventually get any real number you want. So it's 1-to-1, it's on 2. So f is a bijection. Cool. That's step 1. Now I need to make sure that f is continuous and its inverse is continuous. Well, f is just polynomial, so it's continuous. F inverse, just polynomial, so it's continuous.
Yeah. Okay.
So f is continuous, f inverse is continuous.
Yep.
And so this is, in fact, a homeomorphism. So what did I show? I just barely showed that R with the standard topology is homeomorphic to R with the standard topology. Okay, big whoop. We did it with a function that happened to shift and stretch by a magnitude of 3, and that didn't change anything. So this is starting to give you some of the intuition for shifting and stretching doesn't really change anything topologically speaking.
Gotcha.
Okay. Maybe say one more thing about this homeomorphic thing before we go any further. Going back to this definition. I told you, first off, it's a bijection, and then second off, I told you, first off, there has to exist a bijection, and second off, that bijection needs to be continuous and have its inverse continuous. What that's saying, in a more abstract math sense, is first it's saying a bijection existing between two sets means that the sets are somehow equivalent to each other. It means that the sets are the same size.
Yes.
So that's the first thing we're saying. I'm saying, first of all, if we're going to have two topologies be the same, first we need the two sets have the same size, and then second, we need to make sure that our mapping preserves topological structures both ways. So the bijection, one way to think about a bijection between two sets is the same. Those sets are somehow the same size. It's what we mean to say that two sets are in some sense the same. So if we're looking at naked sets, forget topological structures. We're talking about a set and a set. If we say that two sets are isomorphic to each other, two sets are somehow the same, the only thing we can check is their size. It means that they're the same size.
Yeah.
That's what it means for one set to be isomorphic to another set. So in some sense, the set 1, 2, 3 is the same as the set ABC. If there's no structuring down on these things, and we're just looking at those bare naked sets, those sets are in some sense the same.
Can we check the subsets? Like, can we see if 1, 2, 3, the set containing 1, 2, 3 is a subset of the set containing ABC?
Well, if they're subsets of each other, okay, then they're equal, and they're identical, they're the same set. So now, what you're interested in is a relation that means that they're somehow the same, but not identical. So identical is one way that we say two things are the same. Go back and think like in geometry. When I say two triangles are congruent, I'm not saying that they're the same triangle. I'm not saying they're identical, but I'm saying there is some other notion besides identity under which these two things are somehow the same. And so in sets, what's some way that sets are somehow the same? There is identity. Outside of that, a weaker notion of the sameness that we're still very interested in is they're isomorphic to each other. They have the same size. And how do I know that two sets are isomorphic to each other?
Do you find a function that?
There's a bijection between them.
Right.
That's what it means. That's the definition of two sets are the same size. What does it mean for this set to be the same size as this set? The dumb way to say it is if they have the same number of elements and they're the same size. Because then you have to count 1, 2, 3, 4, 5, and then come over 1, 2, 3, 4, 5. That's a dumb way to make sure that two things are actually the same size. Imagine that I was in a massive room full of boys and girls. And I want to know, we'll think about the set of all boys and the set of all girls. Are there the same number of boys and girls in this room? The dumb way to do it is to try and count all the boys and then try and count all the girls. Much easier way to do it is pair off. Did everyone pair off? Oh, someone was left out? Was it a girl? Well, if someone was left out, they're not the same size. If everyone pairs off, I know that there must have been the same many. How many? I don't know. I don't care. I don't need to be able to count them to know that there was the same amount.
Right.
To know that the two sets were the same size. We call it set cardinality. You might remember earlier, I don't know if it was in this class that we did it. I think we did. We proved that the natural numbers have the same cardinality as the integers.
Yeah, right.
So the cardinality of the naturals and the cardinality of the integers are the same. There's the same count. How did we prove that? We constructed a bijection between them. So anytime we're talking about these sameness things, it's very natural that they're a bijection with more added structure. So bijection says the sets were the same, and on top of that, we add more structure on top of that.
Right.
So a homeomorphism, first off, it's going to be a bijection because the sets better at least be the same. And then on top of that, it's going to be continuous both ways. And so it's going to preserve the topological structure as well. And so, I don't know, that's the way I think about this every time I see that bijection. I think, okay, so the sets are the same, and what else? Kind of a big side note for that, but I think it's perfect. Okay, so we talked about how this function right here is a homeomorphism. If you take the real numbers and you shift them one to the right and stretch them out, you didn't change anything. It's still topologically equivalent to what you started with. That's what that says. Okay, So theorem is going to be that this being a homeomorphic is an equivalence relation. Now I don't know if you've come across equivalence relation before. We did this earlier in the class. What does it mean for, well, first off, do you have good intuition for what a relation is?
Yeah.
It takes two terms and it spits out true or false. Less than is a relation. You give it two numbers, 1 and 3, and it spits out true or false. Plus is not a relation. If I give it two numbers, 1 and 3, it spits out 4.
Yes.
So relations, you give it the two terms and it spits out true or false.
Oh, I see what it's saying. Okay.
Okay, so this is a relation on topological spaces. You give two topological spaces, it's spitting out true or false. And it spits out true if they're homeomorphic to each other. If there exists some homeomorphism between them. Okay, so now we're often interested in relations that are also equivalence relations. Equivalence relations are relations that have three properties. It turns out that our homeomorphism relation is going to have this property. Congruence, that you know enough from geometry, also has this property. And we can make up our own relation, has the same height. We'll call that a relation on the set of all people. That would also be an equivalence relation. So what do equivalence relations have? They have three properties. We call the first property reflexive. So if R is an equivalence relation, if R is an equivalence relation, then 1, for all x in whatever our domain is, x is related to x. So that one we call reflexive. So this is the first property. Let's go over it for the ones that we just talked about. So if we're talking about if R, our relation here, is homeomorphic, then this is saying every topological space is homeomorphic to itself.
Oh, yeah, obviously.
We'll come back to that one here in a second. Let's think about it on congruence. If this were congruence, this is saying every triangle is congruent to itself. If we were using the has the same height relation on the set of all people, this would be saying every person has the same height as themselves.
Right.
Okay, so how really quick do we show that homeomorphisms are reflexive? How do I know that every topological space is homeomorphic with itself?
Because you can find a bijection.
What's the bijection? We got to come up with one now if we're going to show it.
It's just itself.
It's just the identity function.
Yes.
So we just use the identity function from the set x to the set x by identity on x is just equal to x. Map every point to itself.
Yep.
Then every open set maps to an open set, and the preimage of every open set is an open set because it's just itself.
Right.
So that's one that's onto maps open sets to open sets, and the preimage of open sets are open sets. Okay, so that's how we argue that every topological space is homeomorphic with itself. That's the first property, reflexive. Second property is called symmetric. Symmetric, what do we show? We need to show that if x is related to y, then y is related to x under our relation. Let's go over our examples, going back to geometry. This says if triangle x is congruent to triangle y, then triangle y is congruent to triangle x. Yes, that's true with congruence. Let's go back to our same height. If Jack has the same height as Jill, then Jill has the same height as Jack. Yes. Now let's go for R's. Is it the case that if I know that my topological space X is homeomorphic to Y, how can I argue that Y is homeomorphic to X?
Because the inverse of the function would be continuous.
Perfect. So this gives me that then there exists F from X to Y such that F is a homeomorphism. But then, if F is a homeomorphism, F inverse from Y to X is a homeomorphism as well. And so, that's how we know that it's symmetric. So that gives me then that Y is homeomorphic to X. Wasn't going to bother writing out the proofs of any of these, but if you haven't seen equivalence relations before, it's good to get some concrete examples. Okay, and then finally the third property that every equivalence relation has is that it is transitive.
Yeah.
So this was reflexive, this one right here was called symmetric. And then finally we have transitive. What does transitive mean? It means that if x is related to y and y is related to z, then x is related to z. That's what it means for the transitive property to hold. So that was the transitive one. Notice, once again, for congruence in geometry, this works. If triangle x is congruent to triangle y and triangle y is congruent to triangle z, then triangle x is congruent to triangle z. Or the same height on people. If Jack's the same tall as Jill and Jill's the same tall as Bob, then Jack's the same tall as Bob. We're trying to prove it in our case with homeomorphisms. Maybe I can just talk through this one. If x is homeomorphic to y, then that means there exists some function f that's a homeomorphism between them. So then I know that there's an f that maps x to y, and that it's a homeomorphism. Similarly, if y is homeomorphic to z, then I know that there's a g that maps y to z, and it's a homeomorphism.
And then we can use our function composition for moving.
Exactly. Then f composed with g is going to be we didn't prove this, it's kind of not, I don't know if we proved it in the preliminary stuff, but the composition of two bijections is a bijection, that's the case. So f composed with g, it's a bijection. We just barely showed that function composition, that if two functions, it's right here. If two functions are continuous, then their composition is continuous. So f composed with g is going to be continuous. Since f is a homeomorphism, f inverse is continuous. Since g is a homeomorphism, g inverse is continuous. And so then the inverse of the composition is also continuous.
Yes.
And so f composed with g, it turns out then, is a homeomorphism.
Right.
So that's how we get the transitive property from this.
Makes sense.
So it is one of these equivalence relations. We have lots of equivalence relations in different fields of math. This is the one that we use for topology. And so there's lots of relations out there that end up being these equivalence relations. We call them equivalence relations because they, in some sense, are saying two things are equivalent. If, in some sense, two things are equivalent, then they're going to satisfy these three properties, if they're somehow the same.
Right.
And so that's what equivalence relations capture. So very common to say this is an equivalence relation. If you're in my geometry class, one of our postulates would be congruent is an equivalence relation. It's one of the postulates. And that's what it means. It means it satisfies that, and that. Okay. So enough with that. Let's get into some more feel-good examples. So let's start showing all sorts of things are homeomorphic to all sorts of things. So first thing I'm going to show you now is that the real numbers with the standard topology are homeomorphic to just the interval -1 to 1. Or in other words, if we had the interval -1 to 1 and we stretched it out from -infinity to infinity with the same topology, topologically speaking, we haven't changed anything. So the entire real number line R and the open interval -1 to 1, given them the standard topology, are homeomorphic. They're the same topology. That's what we're going to prove. How do I prove that this is homeomorphic to this? I need to come up with the function between them. That's a bijection. And it's continuous, and its inverse is continuous.
Yes. Right.
Here's where our function is going to be. Our function is f of x is equal to x over 1 plus the absolute value of x. Let's get a little bit used to this function. We'll create a quick table over here. If I plug 0 into the function, what do I get?
1. Or,
I get 0 divided by 1,
yeah, right.
which is 0. If I plug 1 into the function, what do I get?
1/2.
1/2. I get 1 over 1 plus 1. So I get 1/2. If I plug -1 into the function, what do I get?
Undefined. Oh no, it's absolute value of x. Sorry.
Yeah, that's absolute value. So we get -1 over 1 plus, what's the absolute value of -1?
1.
So we get -1/2.
Okay. Yep. Okay. Sorry.
Minus 1/2. If I plug 10 into the function, what do I get?
5.
10,
10 11.
10 over 11. If I plug negative 10 to the function, what do I get?
Negative 10
Negative 10 over 11. And as I plug in bigger and bigger numbers, the function gets closer and closer to 1. If I plug in 1 trillion, I get 1 trillion over 1 trillion and 1.
Of course.
Stupid close to 1.
Yes.
Similarly, if I plug in really small numbers, really negative numbers, numbers far down the negative part of the real number line, then we get closer and closer to negative 1.
Okay.
And so what this function looks like, if we were to plot it out, it looks like this.
Okay.
Now it's an always increasing function. And so no two inputs can go to the same output. If I have two different inputs, it has two different outputs.
So it's bidirectional. Or
So it's 1 to 1.
1 to 1, sorry.
Is it on 2?
Yes.
It's contained between negative 1 and 1. How can it be on 2? We never get 5 to come out of it. Is this function on 2? Can we use up our entire codomain? Yes, our codomain was negative 1 to 1. Our codomain is not the real numbers. Okay. So, we're arguing that f from here to here is a bijection.
Okay.
Okay. So, it's 1 to 1 and on 2. Hopefully you see that now.
Yes.
We'll get arbitrarily close to 1. We'll get arbitrarily close to negative 1. We'll never quite get there.
Why did you say? Oh, never mind. Yeah, answer my question.
Okay. So we get arbitrarily close to 1. We get arbitrarily close to negative 1. So we do get this whole interval, right?
Yep.
And on top of that, it's 1 to 1. Okay. Hopefully you can see that just from the fact that it's increasing. I think that's the easiest way to see it. But you could also think about it. If I gave you an output, could you find the associated input? And will always be a unique number. And the answer is yes. Okay. So this is 1 to 1 and on 2. Now, is it continuous?
Yes.
The only thing you have to worry about when you're taking a quotient of two polynomials is, are we ever dividing by 0?
You're never.
And it's impossible to divide by 0 because our denominator is always positive.
Yes.
So we're never dividing by 0, so our domain is good. Or if we just think about the picture of the scene, using our calculus intuition, we never had to pick up our pencil to draw that thing.
Yes.
So it works that way too. But, or you can think about it, that's continuous, and that over that's continuous because we didn't break the domain. 1 over x is continuous except for at the point 0. We never allow the denominator to be 0, so we're good. Okay, so here we go. This thing is a homeomorphism. So R is homeomorphic to the interval negative 1 to 1. Topologically speaking, they're identical.
Makes sense.
And so that gives you great sense for stretch all you want. It doesn't change anything. Or compact all you want. It doesn't change anything.
Wait, what's the inverse of that function?
Well, we don't want to write it out because we have to deal with an absolute value.
Oh. Okay. But it is continuous.
But it is continuous.
Okay. Alright.
Okay, so I really quick want to show you. This one seems pretty obvious now, but I just want to write it out explicitly just for the sake of completeness. I want to show you that negative 1 to 1 is homeomorphic to any open interval AB with the standard topology on the real numbers.
Yes. Right.
So that's what I'm going to show you next. So the function I used to do that is a function, f of x, is equal to 1 minus x over 2 times a plus 1 plus x over 2 times b. So here's a function that we used to do that. Notice that when I plug in negative 1 to this function, what do I get?
1.
1 minus negative 1 is 2. 2 over 2 is 1 times a is a.
Yeah.
Okay, plus, now we have over here, 1 minus 1 is
0.
0. So this goes out.
Yeah.
So when you plug in negative 1, a comes out.
Okay. Gotcha.
When you plug in 1, b comes out. And then notice that this function is always increasing. The bigger number you plug in, the bigger value comes out. So we can get a, we can get b, we get, and we're always increasing, so it's going to be 1 to 1 and on 2, is essentially why I'm trying to make it intuitive there. So it's 1 to 1 and on 2, so it is in fact a bijection. Now, is it continuous? Well, yes, obviously, that's a polynomial. And then its inverse is also going to be continuous. We can calculate it, but its inverse would also be continuous. Since it's just going to be a function, it's going to be a line of some sort, not including its endpoints. And so, that shows us that every open interval, -1 to 1, is also homeomorphic to the open interval a to b. Now I know -1 to 1 is homeomorphic to R, and I know -1 to 1 is homeomorphic to any open interval AB. So now R is homeomorphic to any open interval AB using the transitive property here.
That seems important.
Huh?
That seems pretty useful.
Well, we're going to have a whole collection of them now, and you're going to see that they group together almost exactly how you expect. Any questions before we move to the next board here?
Seems like you can almost get any function homeomorphic to another set with the right function, is what I'm going to say.
With the right function, if it's possible, if the two sets are in fact homeomorphic, if our two topological spaces are homeomorphic, then yes, it's always possible to find a function to show it.
Yes, it's right.
Now I'm curious if there's a function or
Here's what would be impossible to do. Create a map from -1, 1 to the closed interval AB.
Yeah.
That's 1 to 1 onto, and continuous, and its preimage is continuous. Here's what would be impossible. Because it's going to be real awkward, which point do I map to A? I'm probably,
How do you?
if we think about this same thing here, so -1 still goes almost to A, right?
Yeah. Wait.
it does go to
It does go to A.
Sorry, -1 goes to A, but this interval goes to this interval. So we never quite map to A using this, right? We just get really, really close to A. And we never quite map to B using this, we just get really, really close to B. Notice that we were going from here to here, so we never actually plug in -1. And we never actually plugged in 1.
Right.
But that's a small technicality.
Yes.
This also shows that the closed interval, -1 to 1, is homeomorphic to the closed interval A to B.
Yes.
It also shows that, same function. You just extend your domain and codomain a little bit. But extending this to include -1 and 1, and not extending this to include A and B, now I need to map -1 to something. And I can't map it to A, because A is not included over here.
That's what I even know.
So if I try doing, here's what I'm saying would be impossible. If I'm trying now, I'm going to say, our domain we're going to include -1 to 1. But we're trying to just map to AB here. So I can't actually map something to A.
You can map something to A, can't you? You can't map something from -1 though.
I can't have -1 mapped to A.
Yes.
-1 has to map to something in here. So now my function's broken. I can't use this function. I gotta come up with some other function.
But you can't find any functions yet.
You can search to your heart's content. A lot harder to show it's impossible than to show it's possible.
Yeah, right.
Because to show it's possible, we just gotta think and come up with that clever example. To show it's impossible, you try and be clever and find out, oh crap, that didn't work. Try and be clever, oh crap, that didn't work.
Yeah, right.
And that's a cycle. Or you can find clever ways of proving it, which we'll eventually get to. Properties you can look for. So when we get to talking about topological properties, we're going to find out that these homeomorphisms preserve these topological properties. And so you can just check, does this function, or do both these topological spaces have this property? And if they don't, then no homeomorphism could exist. So that will be a way that we kind of roll it out.
Yeah, that's smart.
It's very similar to like, you have your congruent rules in geometry, like side angle side, side side side, all those. You know, if it has these properties, then they're congruent. Is that not getting the edges? I can't tell if my screen's just dark or I'm not seeing it. I think we got it all. Okay, so our next example here, in the standard topology on the real numbers, we're going to consider 1, all open intervals. So any open interval A to B, or any open interval -infinity to B, or the open interval AB. What did I? Not sure what my brain was thinking. A to infinity, or the open interval all of R. Sorry, all of R is included up here. So all these open intervals, it turns out, are all homeomorphic to each other.
Okay.
With the standard topology on the real numbers. Now we've already showed that AB is homeomorphic to R, right? So now I need to give you intuition for these open intervals that kind of only include half of it and not the other half.
Okay.
So I'm going to really try to give you intuition for how these things are homeomorphic to R. How one's homeomorphic to R, and then the other one you kind of get for free. So I'm going to show how R is homeomorphic to one of these. I'm not sure which one I'm going to pick. I'm going to pick this one. So I'm going to show R is homeomorphic to a half open interval like this, one that's halfway infinite.
Okay.
Okay, so let's do that one first, then we'll move on to these other ones. So here's the homeomorphism that we're going to use. We're going to map R to the interval a to infinity. I'm going to create F, so F is a bijection, continuous, and its inverse is continuous.
Okay.
So here's how it's going to map. It's going to map to e to the x plus a. Now that e, I don't know, you all comfortable with e? It's just a number. It's just the standard constant that we use anytime we want to talk about an exponential.
Yeah.
We could have just as easily used the function, I could have used 2 to the x plus a. Doesn't change anything. I could have used 17 to the x plus a. These are all going to work.
So you just.
I chose e to the x plus a.
For fun.
Yeah, I just needed something that never quite gets 0. I need something that's always positive, but is never quite 0. It gets arbitrarily close to 0, but never quite 0. And that's what exponentials do. Think about 2 to the x. What is 2 to the negative 1 equal to? 1/2, right?
Yeah.
2 to the negative 2, what's that equal to? 1/4. 2 to the negative 10, what's that equal to? 1 over 1024.
I'm not good with my expression.
How say Farley would know his powers of 2?
Nope.
Oh, you don't? Never had to read a lot of binary?
I know, as a coder, it's barely needed. It's more just interesting to me.
We do have quite a few things with bit shifting
Do you
for
really?
values. Yep.
That's cool. You guys decide on the obsession with efficiency or what?
Or it works out really nicely.
Wow.
So there's a couple places where it works out nicely that way if you just do it that way.
I'll have to go
Like what are you trying to do? Well, that's the same thing as just bit shifting. Let's just do that.
I'll have to go study it a little more.
Well, anyways, the point is, the bigger negative number I put here, so by the time I put something like 20 up here, now this is roughly 1 over a million. It gets really, really small, but never quite 0.
Yeah.
Because it's going to be the same thing as 1 over 2 to the 20. Right? That's the same thing as that?
Yep.
And so, it gets smaller and smaller, but never quite 0. That's the point. So, I just stuck some exponential in there. I chose e to the x. Could have been 2 to the x. Doesn't matter.
Okay.
So, here's a number that if you plug in a number arbitrarily close to negative infinity as your x, this gets arbitrarily close to 0, but never quite 0. Just really, really close. Right? Okay. So, notice what this function will spit out. I can spit out any number as big as you want. You want me to spit out 10,000, I can get to spit out 10,000. But the smallest number I can possibly spit out is a. Because the smallest this can ever be is 0, but not quite. And so the smallest thing I can ever get to spit out of this is just a little bit more than a.
Yeah.
So this function spits out just slightly more than a, not quite a, but it gets as big as you want.
Okay.
And it does so in a continuous way. If we were to draw the picture of this thing, it would look like this.
Yep.
It gets arbitrarily close to a as we go that way, getting closer and closer. As we go this way, it shoots off. Right? If we look at 2 to the 20 on the other hand, that's a million.
Yeah.
Okay, so here is our function that shows that this open interval is homeomorphic to this open interval with the standard topology on the real numbers. Remember, it only makes sense if we're talking about the topologies. You can't just say one set's homeomorphic to another set. That makes no sense. Right? They have to have associated topologies for this to make any sense. Okay, let's look at our next example. All bounded closed intervals, A to B, are homeomorphic to each other. So the closed interval 1 to 2 is homeomorphic to the closed interval negative 10,000 to 286,000.
What do you mean bounded?
They don't go out to infinity because all of R is also a closed interval.
How do you close infinity?
It's not a bounded closed interval. It's just a closed interval.
Oh, right. Yeah, right. Okay.
R is both closed and open in the standard topology.
Sorry.
Right. So a bounded closed interval means no infinities allowed.
Okay.
Because notice that R was already turned out to be homeomorphic to the stuff up here.
Yeah.
So it's not homeomorphic to the stuff down here.
Right.
And you kind of run into the same problem. Why? So we knew how to create a homeomorphism here between -1 and 1 and R. If you try to include the endpoints, that's kind of like trying to figure out, okay, what do we map infinity to and negative infinity to? Right? But those aren't actual numbers, so we can't actually map to them. So that's the problem you run into when you try and treat R as homeomorphic to one of these intervals. You end up trying to map A to negative infinity and B to infinity. And there's just no way to do that.
Can't do that, right?
That's just intuition. So all our closed intervals, A to B, it turns out are all going to be homeomorphic to each other. Okay, let's prove that one really quick. I'm just going to create a simple function. I'm going to show that the closed interval 0 to 1 is homeomorphic to the closed interval A to B. Here's my function that's going to do that. Just a simple line. Here's its slope. Its slope is B minus A, whatever that is. And its y-intercept is going to be A. So it's just a line with y-intercept at A, but it's only defined on the interval 0 to 1. So 0 goes to A, 1 goes to B. Here's our whole function g. It's just a line, but it's only defined on the interval 0 to 1. That's our domain. So obviously just a line that's continuous. Its inverse is continuous. It's a bijection. And so there we go. So I just really showed that this is homeomorphic to any interval. Pick any other interval. Well, it's homeomorphic to 0 to 1, which is homeomorphic to any interval. So I showed any bounded closed interval is homeomorphic to the closed interval 0, 1. And through transitivity, they're all homeomorphic to each other.
Yep.
Perfect. And we already talked about the picture. Okay, finally, all half-open intervals are homeomorphic to each other. Now, how those are homeomorphic to each other, that's an easy one to do. Just flip the signs on everything.
Oh.
Right? Assign A to B and assign
Oh, yeah.
B to A.
Okay.
So this to this I'm not going to worry about, but these to this might be a little less intuitive. So that's one we're going to map. So I'm going to show you that the open interval A to infinity is homeomorphic, the half open interval A to infinity is homeomorphic to the half open interval negative infinity to B. And it's still going to be intuitively exactly what you think. Basically, flip it around and line up the A with the B. That's essentially what we do. So what is my h function here going to be? It's going to be negative x, flipping everything around. And we add on the A and the B. What does that give me? That makes up when I plug A in, it spits B out. So if I plug A into this function, negative x plus A, cancel out, and we're left with B. So I made A map to B, and then we just get smaller from there. As you plug in bigger values for x, your image gets smaller values. So the biggest thing we can get to come out of here is B. And we get that when we plug in A. We can only plug in numbers A or bigger, and so the numbers that come out will be B or smaller.
Right. Yep.
As you plug in a bigger x, your whole output gets smaller.
Yep.
Because x is a negative number.
Right.
You see it?
Just keep going.
Let's just say it again. I think you'll get it. So we're mapping all the numbers from A. So the numbers that we're plugging in, we're starting at A, and then we're just plugging in bigger numbers after that. That's what we're plugging in here. What we're plugging in here is all the numbers from A going up. That's what we plug into the function. When I plug A into the function, notice that, so plug in A for x, we get negative A plus B.
Oh.
So it just spits out B.
Yep.
Okay, so notice that when we plug in A, we get exactly B out. Now notice what this function is doing. It's adding A and B together, and then it's subtracting x. So the bigger my x is, the more I'm subtracting.
Yep.
So, as I plug in numbers bigger than A, my output is going to be smaller than B.
Yeah.
A mapped exactly to B. When we plug in bigger numbers, our output is smaller numbers because we subtract whatever our input is. So this is going to map from A to infinity to negative infinity to B. And that's essentially what it's doing, is it's just flipping everything around and adjusting as needed.
Right.
And what does that look like? Here's a picture of H. So we map A to B, and then now as we map in numbers bigger than A, as we plug those in, we get smaller outputs. And this should just have a slope of -1.
Yeah. Okay.
Okay, so there's some feel-good examples. Seeing how a bunch of different topological spaces that we're already familiar with are all homeomorphic to each other. Standard topology on that is logically equivalent to standard topology on that is logically equivalent to standard topology on that. They're all equivalent topologies. Topological spaces, I should say. Okay. Let's do another example. You good with radians?
Been a while.
Do degrees is what you're saying? Well, do degrees. Makes no difference. 360. 360.
360 is 2 radians.
2 pi radians is 360 degrees.
Oh, 2 pi radians.
Yeah. Remember, a radian is how much the radius covers of the arc length. How many radiuses do I need to get around the circle? 2 pi.
Yes.
So there's 2 pi radians in a circle. But we can use degrees if the radians might throw you off. It's fine. Makes no difference. Alright, so here's what we're going to do. So we're going to look at the half open interval 0 to 360 and then S1, which is the circle. And we're going to view them as subspaces of the standard topology on R and the standard topology on R2.
Okay.
This is just a portion of the real number line. So it's just a subspace of just R. A circle, on the other hand, we need 2 dimensions to draw. So it's going to be a subspace of R2. So here's our picture of those. Here is 0 to 360, just some portion of the real number line. Here is S1, a circle.
Okay.
Some portion of R2. This is in R1, this is in R2. They have the standard topology. What do open sets look like over here? You take open intervals and intersect them with the set. And whatever comes out is open over here. What's open over here, take open balls and intersect them with the set.
Okay. Yeah.
Because they have the standard topologies. So over here, what's open? Open intervals intersected with the set. Over here, what's open? Open balls intersected with the set.
Oh yeah. Oh yeah. Okay. I thought that said subsets. Sorry.
So in other words, since what I'm about to draw, since that shape is open in R2, then where it intersects the circle, which is the interval from here to here, will be open on the circle.
Right.
Because they're inheriting this, they are getting the subspace topology from the standard topology on R2, and this is getting the subspace topology from the standard topology on R1.
Right.
So on here, if I take any open interval in R, so some interval like that, and I intersect it with that set, the result is going to be open in this topology. So we're mapping from a topological space to a topological space.
Okay.
So our function f maps from 0 to 360. We're not going to include 360 since we're basically going to map it to where that point lands around the circle. And since 0 already maps here, we don't want to map 360 to there as well.
Okay.
Otherwise, we're not going to have a bijection.
Yep.
Oh yeah.
So that's why we're not including the sample. So we're going to map 0 to 360, not including 360. And our mapping just takes it and it marks the point off on the circle associated with that angle. So 0 gets mapped here, 90 gets mapped to here, 180 gets mapped to here, 270 gets mapped to here.
It's driving me nuts. Why? Okay. One dot is missing in that infinite. Okay. Never mind.
Because we already included that dot when we mapped 0. If we also include 360, we would map to the same point. And then I'd have 2 points in a domain mapping to the same point over here.
Which wouldn't be one.
Which would make so it's not a bijection. We want it to be a bijection.
It's not a bijection and it's not a circle.
Well, it would still be a circle.
No. Well,
Yeah, it's just we would have 2 points mapping to the same point.
Yeah. Yeah. Right.
I would just have 0 maps to there and 360 maps to there.
Mm-hmm.
If I had you standing on the edge of the circle, if you start there and I say, I want you to move 0 degrees, and I say, okay, and I want you to move 360 degrees, you both end up at the exact same point.
no, but here's the thing. We don't have 360. We have up to 360. So
I'm saying if you did include 360,
if we did, it wouldn't be a circle. I'm saying this is not a
hold
circle.
on, it would still be a circle. Maybe I heard you wrong.
You're saying that if you do not include 360 degrees, it is not a circle.
Oh, you're saying you have to include 360 for it to be a circle.
Yeah, 'cause they have to.
Okay. So we are the only number we're missing is 360, right?
Yep.
Okay. 360 maps to this exact point right here. The exact same point 0 maps to.
And we don't have 360.
Hold on, but we have 0.
Yes.
And they map to the exact same point. Did someone map to this point? Yes, 0 did. So we don't need 360. We already got covered with 0. We also don't need 270 degrees.
No, that doesn't.
Or
make
720
sense.
degrees. Pick any point you want over here. It was mapped to from a point in here.
That's like saying I can map any of the numbers to anything, to any of the other ones. Why is up to 360? Okay, let me think about that for a second. Why is 0?
Let me try and walk you through an argument that I think you could accept. So imagine we use the closed interval 0 to 360 exactly.
Yes.
So then we would have started at this point and gone all the way back, and we would have included that point twice.
Yes.
This point gets mapped to twice, every other point gets mapped to only once.
Yep.
Now, if I just subtract the exact point 360, so that's the only point I removed. This is an infinite set.
That's correct.
I just removed that one point. So now we're only mapping to it once instead of twice.
You can't map something unless there was two numbers that became one. You can't just say this number and this number are connected now. It doesn't.
Oh, you're thinking about some quotient space and we're gluing points together.
Yes.
We're not doing that.
Okay. What are you
Okay.
doing?
Okay, I get your confusion now. We are simply showing that I can find a function from this interval to this circle that's 1 to 1 and on 2. Continuous, and its inverse is continuous. So I am not taking a quotient map here. I'm not doing a quotient map to get the circle. If I did the quotient map, you're right. I need 2 points to glue together to identify as the same point.
Actually make it a circle. It's not a circle. It's just a line. It's like grabbing a string and going like this and not actually connecting them. You're like saying, here, look, it looks like a circle.
I get what you're saying. I get what you're saying.
Okay.
So your intuition comes from when we do a quotient map.
Isn't that?
And a quotient map is like changing one topology into another topology.
Yes. That's kind of what we're doing, aren't we?
No.
So, okay.
We're saying, are these two topologies the same? We're asking a question. Is this somehow the same as this?
I agree they are the same. I just don't.
Well,
think
let's
it's correct
analyze it.
to
Let's
say
not
that.
jump the gun. Let's see. Let's make sure it has all the properties. So forget is the same, forget any of that stuff. Let's just check, manually check, does this function have these 4 properties? That's all we're checking.
Great, but it's not a circle.
This over here is a circle, by definition.
No way, it can't be. It's missing a point.
This circle has nothing to do with this function over here. As in, forget the function, forget that interval. They're gone. We start with the circle here. There it is.
Okay.
Okay, I come over here and I also create this number line. I don't include 360.
Okay.
What am I trying to do? I'm trying to come up with a function from here to here that has 4 properties. And just to see if I can do it. So here's the function that I'm going to come up with. The function is going to take that point 0, and it's going to map it, it's going to pair it with the point right there. Those are put together in the function. 90 is paired with that point. 180 is paired with that point. 270 is paired with that point.
Okay. Alright.
359.99999 is paired with that point.
So there's not a single point we haven't accounted for.
So we've accounted for all the points. That's all we care about.
I see.
Okay, good.
Because they're two completely separate. We're just trying to say that they're the same, but we're not actually creating a whole nother. Okay, I got you.
Not doing a quotient map. We're not changing one topological space into another.
Okay, that's what I thought. Okay,
Yeah, once you said that, I got your confusion. Okay. So now, here's our function. We didn't write it out explicitly. If I did, I'd have to write in polar coordinates. I wasn't sure if you were comfortable with polar coordinates. If you want it in polar coordinates, in case you care, that would be we map each point to, we just give it a radius of 1 and the same thing then. There it is in polar coordinates.
Oh, yeah.
But if polar coordinates throws you off and you get the picture of what the picture's talking about, this is just about feeling good. This isn't about, let's talk about polar coordinates.
I don't know what that is.
Well, that might be a problem then. If you don't even know what it is and it's just that you're not comfortable with
What did
it.
you say now?
Polar coordinates?
Polar. Oh, I know polar. Yeah,
Just using r's and thetas rather than x's and y's.
I wrote in CNC machines and used polar coordinates.
Okay, perfect. So if you think about this in terms of polar coordinates, radius 1, here's your angle. So we're doing all the points at distance 1 from here, marked off at different angles. Okay, perfect. So that's exactly what this function does. So we can see it's 1 to 1 and on 2, right? Every point goes to one and only one point, and we used up all the points.
Yes.
Now, is the function continuous?
Yes. Yeah.
Yes.
How do we check? We pick some random open set over here and check its pre-image. So hopefully purple can kind of draw. If I were to go and I were to take some open set over here, so purple, that would give me like this interval from here to here. Can you guys see the purple?
Yeah.
Kind of hard to see. That open interval, if I look at its pre-image over here, it's going to be like this interval right here. Open set over here, look at its pre-image, yep, it was open. Let's pick the only hard one. Imagine I pick the open interval to overlap this point. So I do this, that is just awful. Make the brown show up okay. So I do that open interval and I look at its pre-image.
Well, that's just.
Its pre-image over here is going to be, let's see, those points are these points right here. So that's going to be these points right here, up to there.
Just union with the other ones.
Union together with the points over here at the end, right?
It's just a union of open sets, isn't it?
Yep, that is open, that is open.
Yes.
So it's a union of open sets, so it works. So f is continuous. What about its pre-image? Is its what about its inverse? Is its inverse continuous? So if we were to look at, well, I guess we can keep calling that f. But if we were to look at now f inverse from here to here, is that function continuous?
Yes.
And the answer is no.
What?
And I was hoping you would see it. Look. Here, this point and this point are close.
Ah, I see it.
Over here, this point is right there, this point is right there. They are no longer close.
You're right.
Proximity is not preserved. Or in other words, if I take the pre-image of open sets here, they're not going to be open here. Let me show you one. So this set is open over here. Because it's an intersection of an open interval with that set. Let's look at its pre-image. Its pre-image over here is including this and then rounding around to there. I can't represent that as an open ball.
Yes, right.
So it is not continuous. And thank goodness it's not. Because we use homeomorphisms to say two things are somehow the same. And topologically speaking, this and a circle better be very different from each other. We definitely want that to be the case. It was bugging us the whole time that you kept thinking we were saying somehow they're the same. You're saying, no, they can't be. And you're right, no, they can't be.
Interesting. So it's because they connect at that end, but don't connect over there. They're not homeomorphic?
Right, so
Right.
the topologist way of viewing this is instantly check. Are there points close together here that aren't here? Or are there points close together here that aren't here?
Yeah.
That's what you quickly do. You check proximities. If they don't have the same proximities, nope, not homeomorphic.
Right. Okay.
So let's get through. We'll just do some pictures to get things comfortable. Do the punctured sphere. Do one more thing I want to show you. We'll worry about the rest of that for later. We'll just talk about pictures now. So some other things that are homeomorphic to each other. The entire real number plane, it turns out, is homeomorphic to the half plane. Randomly pick a line to divide the plane in half, and this is going to be homeomorphic to this.
Yep, makes sense.
And the way you see that is leave the y's alone, and you just map x to e to the x plus a. So when you do it under this mapping, pick a point over here. When you map it, you give it the exact same y, but now its x gets compacted. And it's the exact same logic that we used over here when we said all of R is homeomorphic to a to infinity.
Right.
So in the x direction, we compact it. In the y direction, we left it alone. Doesn't change anything.
Yeah.
This one, you can kind of see how this is also homeomorphic to this. How do you see that? Well, remember, all of R is homeomorphic to just some open interval. So we map all of R to some open interval, and all this R to some open interval.
Why, we could just say we map R2 to some open balls, couldn't we?
Well, here's the exact mapping, if you want the exact mapping. So this is using polar coordinates. We map R to R over 1 plus R. So notice that this is doing the exact compression we were doing over here. We take all our radiuses, and no matter how big they are, I'm going to make sure they're all within 1 unit. So you pick any point out here, now in terms of polar coordinates. So it has a radius of R, and it has an angle of theta. When we run it through this mapping, it's going to take that R and rescale it down. Keep the theta the same, but just scale all your radiuses down so that they never get bigger than 1.
So basically, a square and a circle are homeomorphic.
A square and a circle are for sure homeomorphic. The more interesting ones are these infinite. We went from something infinite to something completely contained.
I'm imagining those infinite planes as just squares. Like they're
Oh.
they're infinitely large squares.
But
That's one way to think about it. But actually, it's also homeomorphic to just like a contained square like that. Talk about the points in between.
I mean, I don't know, infinity and that thing, same thing.
Very different things, but surprising that they're homeomorphic.
Okay.
how is that useful?
we can't. I instantly thought of, there's ways in geometries that we represent geometric figures in like hyperbolic geometry spaces where we somehow project all the real numbers, the real number plane,
Yeah.
onto that
Yeah.
as a way to picture it.
Yeah,
And it preserves continuity,
I can see that.
but it completely changes distances. We crunch up distances. So if I underwent this mapping, then notice that 2 points, which were, billions of units apart, over here are now just like right next to each other. So it completely distorts your distances, but makes
Still,
proximity is preserved, continuity is preserved. Distances are not preserved. Points that were 100 units apart could now be a half a unit apart.
I see the difference.
But points that were 100 units apart weren't right next to each other. And if they're half a unit apart, they're still not right next to each other. There's still infinite distance between them.
Right. Yeah.
So here's one that's probably pretty intuitive. The surface of a cube is homeomorphic to the surface of a sphere. Here's the way I like to think about these ones.
Makes total sense.
I like to think about it as viewing the sphere as kind of like a light source. So imagine this was a light source actually giving light off from its surface, and I stuck it in this room, in the very center of this room. Imagine this room was a perfect cube. And I think about each point where the photon shoots off from the light source as where we map that point. It would illuminate the whole room. Every photon goes to exactly one point. And if I were to draw some open ball on this surface and look at its projection, it would still be some open figure.
Yes.
So that's intuitively how I like to think about as light sources. So that's how we get the surface of a cube, C, is homeomorphic to a sphere.
Makes sense.
Last one that I wanted to do, well, second last one more, which is a strip of paper that I think you'll like. But quickly talk about the punctured sphere. Okay, so with this one, taking something like this sphere, I'm trying to show that the punctured sphere is homeomorphic to the real number plane.
The real number, okay.
Yes. So we've got my punctured sphere here. In terms of rubber sheet geometry, here's what I'm doing. I'm taking my sphere, I'm puncturing a hole at the top. So I remove just a single point. I've got a sphere, I remove just a single point. And I grab that hole, and since in rubber sheet geometry here, everything's infinitely stretchy and you can't rip it, right? So I'm gonna take that little hole that I made, I'm gonna stretch it. I'm gonna tear it open, I'm gonna flatten out my cube, taking that hole and just stretching it as big as I can. So as I grab this hole and I stretch out the top half, the bottom half is gonna start leveling out. And I can easily stretch out that top half into a flat disk like that, right? And the flat disk is homeomorphic to all of R.
Yep.
So that's,
Where'd the point go?
that one point was punctured, it was removed. So we're not mapping the sphere to all of R.
Oh.
We're mapping the sphere, but with 1 point removed. And now it's topologically equivalent to R. We had to get rid of 1 point.
Was it not equivalent before?
No. And intuitively, why we have to do that is I need someone to start stretching it out.
Oh, that's so cool.
So here's the way that this mapping works. Tried really hard with the picture. Try and explain what my picture's doing here. So I'm gonna have a hole at the top, I have my sphere, and then this brown part, the real number plane, is going like through the equator.
Yeah.
That's what the picture's trying to represent here. Our mapping is going to be, pick any point on the real number plane you want. So I pick the point right here. Remember, the plane's going through my equator right here. So pick any point on the real number plane you want. What point do I map on the sphere to that? So take that point and then draw a line that goes straight to my missing point at the top. Wherever that intersects the sphere, that's the point that I map out. Or we can think about it the other way. Pick any point on the sphere P, construct the line that goes from our hole to P. Notice that that's going to be inside the sphere. And then here's where it comes out. And then keep going. And wherever it comes out and intersects the plane, that's where we map P to.
Wow.
So that is going to map the top half of the sphere to the whole real number plane outside of the sphere.
The whole real number plane?
The whole real, not the part inside the sphere, but the top half of the sphere gets mapped to everything outside the sphere. Because there's part of the real number plane inside the sphere still that we didn't map to.
So we have a giant hole in our square,
We have a hole right here so far.
in our plane.
We're still going to use the same mapping, but notice now, the bottom half of the sphere just gets mapped to the plane where it intersects in here.
Wait, this is an empty sphere, I assume.
Oh, you just
Yes,
put that one at the
sphere, we're just talking about the surface. Good.
It seems like
So the bottom ends up getting mapped up here, because if I do a line straight from here to intersect a point down here, it's going to intersect the real number plane at a point inside the sphere.
yes.
So the bottom half ends up getting mapped inside the sphere, to the portion of the real number plane inside the sphere. The exact equator just gets mapped to itself. And then anything above the equator up here ends up getting mapped to outside the real numbers. Or outside, the real number plane outside the sphere.
Yeah.
So the top half maps to everything outside the sphere, the bottom half maps to everything inside the sphere, and the equator gets mapped to the equator.
Yeah.
And that's the projective sphere.
Punctured sphere.
I mixed that up with the projective plane, because they're pretty similar. So the last thing I wanted to talk to you about, really quick, should have done this before, just need one side that we color on, that you can easily see. Okay, so going back, and we were thinking about the Mobius strip, right? So the Mobius strip is what happens if I flip one side like this, right?
Yep.
If I turn and glue like that, then now we have a figure that only has one side. Notice if I start on the side that with the line, and I keep going long enough, I eventually get onto the side without the line.
Yes.
And so it only has one side. Now our question is going to be, in rubber sheet geometry, is the thing that I get if I just do this, so I'm just going to call it a cylinder for the sake of being able to name it, is this homeomorphic to what we get, not if we twist once with the Mobius strip, but if we twist twice?
Yes.
Is it still homeomorphic?
Can't see why not.
Now, let's think through this carefully. We think about this in terms of rubber sheet geometry. There's no way for me to start with this and get back to where I started unless I cut and untwist.
Wait, hold on. So you're starting out split.
So I start out like this.
Oh, start out. Okay.
So here's one space where the paper's like this. Probably should have just done two papers. So I start with this, and I end with this.
Right.
And we give them just the topology that they inherit from R3 here.
Sure.
Are they homeomorphic to each other?
No.
I can't see why not, but I mean, I guess they might be, or might not be.
Keeping in mind, there's no way for me to get from where I started, here, to where I ended without cutting and gluing.
Wait.
Well, the thing is like, it's hard to say you even did.
You want to untwist it some way, you can't untwist it.
Yeah, but you're like saying.
It's always got that twist in it.
Sure, but you're saying like.
Well, he's wondering, can you untwist it?
No. I don't.
Okay.
Okay.
So there's no way to untwist it. So we're wondering, is just this shape homeomorphic to? Now we're really going to test my drawing skills. Give myself some space here. And then let's see. And then back up.
What the hell?
Yup.
I'll just give you time to finish.
It might be easier to do like little arrows and stuff.
Probably understand it if we color in one of the sides. So I'm gonna color in the inner part brown. So this is the inner side. And then you see it again right there, the twist.
That makes sense.
And then blue's the outer side. Okay, so that's what we're trying to say.
That makes sense.
Okay, cool. So is this homeomorphic to this?
And it can't be.
I've got to say yes, but I don't know.
Well, in order to make that you have to cut it in order to twist it. Would you not?
But you're putting it back exactly the way it was.
That is true.
But it has that twist in it.
I get that, but what does the topology have to care about the twist? Twist means nothing. Or does it?
Or it doesn't. So we think about this in terms of rubber sheet geometry. As long as you're not cutting anything together or gluing anything together, it should be the same. So we know that. So if I have a shape and I don't cut or glue anything, when it's all said and done, what I'm left with is homeomorphic.
But if I cut it and I put it right back, dude.
But if I cut it and I put it right back, in a way that preserves proximity, it is still homeomorphic.
So it's like if you cut
Notice that all the points that were close to each other, so I did cut it, but after my twisting,
They're still there.
I made sure that all the points that were close to each other are still close to each other.
Yes.
It's gotta
So
be
it is
all-
okay.
So it is homeomorphic to each other.
Yeah.
So there is a stronger notion of sameness in topology
Okay. Then just okay.
that comes all the way down in chapter 12. And with that stronger notion, these would not be the same as each other.
Stronger.
A stronger notion of what needs to be the same.
I see. Oh, okay.
One that does care that it has this twist in it.
Okay.
So there's stronger and weaker notions of sameness,
Right.
Sure.
right? So topologically speaking, using a homeomorphism, these are homeomorphic to each other. Even though you have to cut and paste to get from here to here, proximity is preserved. So the rubber sheet geometry thing can be a little misleading sometimes to people to give them intuition. The best way to think about it is proximity preserved, yes or no? If proximity is preserved both ways, homeomorphic. If it's not, it's not.
Okay.
So that's the way I always like to think about it, in terms of, are the points that were far still far, and are the points that were close still close? So, unfortunately we didn't quite cover everything, but I've already gone way too late. So, sorry about that.
Alright.
So, review homeomorphisms next time, do a few more examples to re-dip our toes into it, and then we're going to shoot off to something completely separate. Metric spaces.
Okay.
So we're going to take a set and give it a metric rather than take a set and give it a topology.